had a good restful weekend and got some outdoors time in to counteract all the video conferencing. This week we have four lecturers giving a bunch of lectures. Laura Reina on perturbative QCD calculations, Adam Martin on standard model effective field theories, Shifang Su on collider physics, and Joe Licken on quantum information science for particle theorists. We'll also have discussion sessions on Wednesday starting at 3:45 TASI time, and that will be Laura Reina and Shifang Su. And then on Friday starting at 2 p.m. because we only have 2 lectures on Friday, and that will be Adam Martin and Joe Licken. And our first lecture, oh, and I guess I should also say we'll continue obviously the coffee breaks at 1:30 TASI time every day. So our first lecture this morning on perturbative QCD calculations is Laura Reina from Florida State University. Please go ahead.
Thank you. And sorry if I kept moving things around. I just wanted to get the right position for me to write. Really glad to be here and to be at TASI again, virtually, at least. I would have preferred to be there in person, but okay. This is, I always liked being there and having interaction with the students. It's typically a wonderful crowd. And I'm glad to be at least virtually back to give lectures here. I hope you have been enjoying this school during the previous weeks. So what I'm going to talk about during these 3 lectures is perturbative QCD calculations. So it's a vast topic and you can reach different levels of details and different levels of somehow learn different things in this realm. But as a probably for most of you, first approach to perturbative QCD calculations, at least at the level of beyond what you can find in every textbook. I think that I gave myself as a goal to lead you to understand or appreciate the impact of perturbative QCD calculations on physical observables, and in particular, I would say where it matters the most these days, which is collider physics. Also because in parallel, you will have lectures on collider physics. So I think it makes a lot of sense for you to reach that level of understanding and sensibility, right? Just to be able to understand where it matters and what it does. So if you wanted to reach, of course, this is the first disclaimer of these lectures. So if you wanted to reach a working knowledge of perturbative QCD, of course, you have to spend time learning more details. But I think it's already a big goal, and it's already very important from the physics point of view to be able to know, for instance, when you listen to your colleagues or when you are about to decide if you embark in a given project or not, if it is relevant and why it is relevant and what does it entail. So here is the plan of my lectures that I pre-wrote in order not to spend too much time writing it down, since there are a few words, and then I will start writing afterwards. During the first lecture, which is today, I would like to review a little bit of the basic elements of QCD. Of course, you must have seen these in your QFT classes, I'm sure. But I want to bring back those points, starting from the Lagrangian, that will set us all on the same, in the same framework. They will give us some framework to discuss what comes next. And in particular, it will give me the opportunity to bring out what are the really important fundamental points that will hit us over and over and will be dressed with a lot of details, but will be fundamentally the same ideas. And so then on the basis of these very simple elements that we will review at the beginning, we will then look at the structure of a perturbative QCD calculation that I will indicate with the PQCD from now on. So as I said, the main focus for my lectures is indeed collider physics, because I think it's where perturbative QCD, it's one of the many frameworks in which you apply perturbative QCD, but it's definitely the one in which it is justified the most applications. And we will take examples in our calculations and in understanding the physics, both from E plus E minus and for hadron colliders, so PP colliders, just to refer to the LHC, which is here now. So once we understand the structure of a perturbative QCD calculation, today we will focus on the easiest part of it, if you want, between quotation marks, which is the hard part of a process, of a QCD process, where perturbative QCD is the thing to use, and there is no doubt about that. And tomorrow we will add both initial and final state evolution. So as we know, QCD and the strong force is also what forms bound states and bound states of hadrons, and those are typically the particle we start with and we end up with. And we will have to understand, however, how perturbative QCD is very important to understand how perturbative QCD can lead us back to the initial state and towards the final state. And we have the tools to study that evolution from perturbative QCD. That will allow us to come towards the end, that could be lecture 3, in understanding the way we operate in developing perturbative QCD calculations. And the fundamental question is, why do we push the order of perturbative QCD? How do we do that? What do we gain? And do we have tools to do that? What is the extent of those tools? And I would like to conclude in the third lecture with some examples that I think are particularly relevant to understand what we have learned, to see it at work, to understand the extent to which we can make sense of the theoretical accuracy with which we can predict certain physical observables, and if that is enough or not. So for your reference, and this will be posted with my notes, I quoted here some literature. Of course, any QFT textbook would probably have at least most of what we will see today, so you can review it there as well. There are dedicated monographs to QCD, right, in particular QCD at colliders, and it goes from the fundamental text by Ellis, Stirling, and Weber about QCD and collider physics to more recent books by Campbell, Houston, and Krauss, the Black Book of QCD. Or if you really want to go to the core of the matter and really understand QCD from one, in particular perturbative QCD from one of its fathers, you take the recent book by Collins, which is called Foundations of Perturbative QCD, and you will have material to learn for a long while. On top of these, of course, you can find wonderful reviews and insights in summer school lectures, starting from previous Stasi lectures to lectures given at the Fermilab CERN school, at the CITEC school, and much more. And I think a point of summer school lectures is also to bring you some working knowledge of things, or some perspective that typically is not what you would write in books, but is nevertheless very important to give you the wisdom in a way, or the experience of people who have worked with it. So this is a little bit also what I would like to do. Today. So again, since this part of my notes is kind of clear, let me show it to you, and then at some point I will start writing, because what I have in my notes is not that neat anymore. But this will save us some time in going through it. So I want to start with really the basic, as I say here. So you see QCD, asymptotic freedom, running masses is what I call it. And the reason why I call it this way is just because this is really the core that I wanted to bring out of our discussion, because the structure of a perturbative QCD process, or the structure of a QCD process in general, a structure of a process that is affected by QCD, is based on these fundamental properties of the theory itself. And so we need to review at least where it comes from. So I would say setting the stage here. So as you know, strong interactions are described by an abelian gauge theory based on the gauge group of SU3, so an SUN group with n equal 3. We call the associated quantum number color just because it's a colorful way of describing it, but it's just nevertheless just a quantum number. And it is built as any other non-abelian gauge theory. So you start, it's a non-abelian gauge theory of Dirac fermions because we take them massive. And then if I just told you these, you'll be able to write this Lagrangian in just 1 second, because it's the way a gauge invariant Lagrangians with a gauge group SU3 or SUN in general made of Dirac fermions is made. There is a Dirac term built in terms of a covariant derivative, and there is a gauge term, which is the usual one. Now, the gauge structure is hidden in this covariant derivative, as is hidden in this strength tensor F mu nu that I've specified here for you. So the covariant derivative is expanded in terms of gauge fields with SU3, in this case, matrices that represent the generators of the SU3D algebra. And the corresponding F mu nu tensor is also expanded on the same basis of generators and has the usual form that contains both an abelian gauge kinetic term and the non-abelian interaction. So you can spend time reviewing if you wanted to try some of the calculations that I propose in the rest of this lecture. So reviewing the algebra of SU3, reviewing important yet not, I would say, useful relations and identities that you use in your calculations. It's not something that we want to do here. What we want to do here is now to remind ourselves that, well, the structure is a little bit more complicated when you quantize the theory. As you know, it's a gauge theory, so it's a theory that has intrinsic redundancy in its degrees of freedom. So when you go to theory quantization procedure, you need to eliminate this redundancy of the integration over the gauge fields. You learned these in QED, you learned these in non-abelian gauge theories, where it becomes a little bit more interesting, if you want, because in the procedure, you add to your Lagrangian naturally, just by implementing this selection of degrees of freedom among your gauge fields, a gauge fixing term that I don't write explicitly because we're not going to do any calculation in any specific gauge here. So I leave it as a gauge fixing. We typically use a covariant gauge fixing because Lorentz-wise is nicer. But when you do this, also you end up having some determinant in the way, determinant of fields in the way that you know how to express in terms of fermionic degrees of freedom that you call ghost. Now these, scalar degrees of freedom that you call ghost. So this part of the Lagrangian of the quantum version of QCD, so of quantum chromodynamics, is the part that is, as we see here, gauge dependent, and that changes slightly your Feynman rules when you go and use them. In particular, it changes the expression of the propagator of the gluon fields that are expressed in terms of a gauge-dependent spin polarization tensor that can be G mu nu, or it can be something more complicated than that, depending on what you have chosen in your quantization procedure, the gauge you have chosen. I haven't written here explicitly, but the presence of these extra term of the ghost terms may add also extra Feynman rules, in particular one Feynman rules, which is the interaction between the gauge fields and ghosts in your Lagrangian that I haven't depicted here, but it appears as related to the ghost part of the Lagrangian as well. And depending on the gauge you use in your calculation, you may or may not have to consider. The other important point that we have to remind ourselves, of course, is the fact that it is a non-abelian gauge theory. So it has these extra p's in the covariant derivative that also affect, of course, the derivation of the Feynman rules from your Lagrangian. And from the F mu nu part of the Lagrangian, you will get self interactions among the gauge bosons that are these two Feynman rules over here that I haven't written explicitly, but I have just drawn to remind you that they exist. And that changes dramatically the nature of this theory. So to move ahead, and I'm still in the neat part of my notes, so I keep using them. Remember just two notes to these statements that I just made before we get to the crux of the matter. First of all, that when the Lagrangian of QCD, this one that we have written here, is embedded in the Lagrangian of the standard model, as it is at the end, because we know the QCD is part of the standard model, this mass term that is totally fine in terms of QCD alone, so when the gauge symmetry is just pure SU3, becomes a problem. And it becomes a problem because our Dirac fermions we started with in QCD now get assigned extra gauge symmetries. They have to satisfy and fall into the representations of extra gauge symmetries, in particular the SU2 of weak interactions. And their left and right quarks, left and right fermionic fields are assigned different representations. So you cannot build a mass term anymore like this. So because of that, you add the extra complications of Higgs interactions through a Yukawa coupling and so on and so forth. So just to make sense for you of why do you hear that mass terms are introduced in a certain way in the standard model, why in QCD they look so natural, and why do a fermion mass term to start with breaks the gauge symmetry of the standard model, why in QCD will not do that. So that is the reason why. The second note that I have here is about, is a general comment. So you have a Lagrangian, which is the Lagrangian of QCD we started from in its classical form, in its quantized form, and now you have to find solutions. And we know that an interacting quantum field theory, finding solutions is particularly hard, if not impossible in a closed form. So we have two approaches to these, and I bring these up because I want to justify the perturbative, the P in my lecture, so the perturbative QCD part of the story. Why do we take a perturbative approach? Well, the two approaches that we have are a numerical approach to the solution of the theory, and an example of these, a remarkable example of these that is that we have for QCD is the lattice QCD, and for which, of course, you would deserve a separate set of lectures just on that, but it is, in its essence, this is what it is. And then you can take, on the other hand, a partial, step-by-step sort of approach, assuming that the perturbation that you add through the interaction is a perturbation, so that the interaction itself is a perturbation, is small, and then you can take a perturbative approach. So you can solve your theory with the usual perturbative QFT approach that you have learned starting from QED on. This is precisely how we will attack QCD in this case, and the reason for that comes from what follows. Well, there is also a practical reason probably that this is just an a posteriori sort of comment. If we could not do that, so if it turned out that the QCD is strongly coupled, even in all regimes, and we would never be able to get a perturbative approach, we would have to go for a numerical solution. Now, if you think to the energies that we are exploring that are of the order of several GeV and TeVs, and you translate that in terms of the lattice parameters, so what we would take to discretize this theory, we would need an enormous lattice in that case, both in extensions and in number of sides. So it would be kind of unpractical to do scattering processes for LHC on a lattice. But we are, as we will see, lucky enough that we don't have to do that, and we can take a perturbative approach, as a matter of fact, which will mean, as I write here, that any observable that we decided to work with in QCD, and of which we decided to calculate the QCD contributions to, will be expanded in a coupling that is the strong coupling of QCD, what I have denoted by G sub S in my covariant derivative here that introduces the fundamental strength of the interactions described by this Lagrangian, which are the strong interactions, what we call the strong interactions, and that we normally reparameterize in terms of GS square over 4 pi in analogy to E square over 4 pi for QED. And then the observable will be expanded as a series in this coupling. So as a series of terms that are proportional to higher and higher powers of the coupling that is our perturbation parameter. So hopefully this coupling will be small, and hopefully the contribution at each following order will be smaller and smaller. Now, this opens the usual question of does this series converge or not? Is this an asymptotic series? Yes, it is an asymptotic series, but remember that we're doing physics, so we are working with objects that have the observables that are measured experimentally, and we have a finite precision with which we can measure these things. So when your theoretical precision is comparable or better than the experimental precision, you have done a job good enough. And the important thing is just to see that the trend is just that each single term that you add to your series falls within the errors of the previous one. So here comes the fundamental point. Here is the beginning, the real beginning of the story, and what the foundation of perturbative QCD, which is the behavior of the coupling. So QCD, as we have described so far in its quantum version of quantum chromodynamics, is a renormalizable theory. It has all the characteristics of a renormalizable theory by power counting and by fact that there are only a finite number of correlation functions of this theory that present ultraviolet divergences, and are the 3-point functions and the 2-point function. So we then can go through the usual renormalization procedure and reabsorb ultraviolet divergences through a redefinition of the parameters of the Lagrangian in terms of physical parameters or renormalized parameters, as I prefer to call them in QCD, for the reason that I will explain in a second. So our coupling GS in our initial Lagrangian and M sub F, the coupling and the masses are substituted by renormalized parameters. And when I re-express that, I will define on the basis of my subtractions, ultraviolet divergences subtraction scheme of choice. And by the time I re-express any observable in terms of the renormalized coupling and masses, all the ultraviolet divergences disappear from my calculation order by order in alpha S. So this is the essence of the renormalization procedure. Then you can re-express it in all the ways you want. You can implement it for your convenience by introducing counterterm in the Lagrangian at the level of the Lagrangian itself by splitting each term into a bare and a counterterm. You can implement it as you like, but this is the essence of it. Now, as I was saying, these renormalized parameters are typically defined depending on the theory that you have at hand as physical parameters or just as renormalized parameters. Now, in the case of QCD, as we will understand later, it is very convenient to define these renormalized parameters in such a way that they are as easy to calculate as possible. And these brings us to define as our preferred renormalization and subtraction scheme, the so-called minimal subtraction scheme of MS bar that you may have encountered in your classes. And if not, we can maybe discuss it a little bit more in details when we meet separately. But the important point of any renormalization procedure, including the minimal subtraction procedure that boils down to just subtract the ultraviolet poles from your ultraviolet divergent correlation functions based on the introduction of some subtraction terms, is just that it depends on a subtraction point. And this introduces a fundamental scale in the procedure that is the renormalization scale. That is a technical scale that is introduced either related to a physical scale or not, but that leaves some scale dependence in intermediate steps of your calculations. Now, unfortunately, the intermediate steps of your calculation here are pretty important because they correspond to the different perturbative orders in the calculations of your observables. You'll never be able to calculate them all. You will always have an approximate calculation. And so these scale dependence that in the full O would disappear stays in the calculations that we do in perturbative QCD. But because of the behavior of this series, its importance should become less and less. And so the dependence on the famous dependence on the renormalization scheme that comes in right here should be controlled or for well-behaved QCD quantities, for well-behaved observables or observable that have been calculated in QCD at high enough precision to make them well-behaved should be just within the errors of the theoretical approximation that typically are at the next order that you calculate. Now, These renormalized parameters are functions of this scale. We say they run. So the QCD coupling runs. It's a function of the renormalization scale, and the masses run as functions of the renormalization scale. And we know how they run because we have knowledge of the relation between the renormalized parameters of a theory from a scale to a different scale. Those are given by a set of differential equations that we call the renormalization group equations that just impose precisely this fact. So impose that the parameters of our initial Lagrangians were scale independent. Our renormalization procedure has introduced a scale dependency in the renormalized parameters, but we have to recover if we could express the original parameters in terms of the renormalized one, the originally in scale independence. So this is reviewed for you briefly on here, where, however, I focus on the main player, which is really the running of the coupling of QCD, which is expressed by the renormalization group equation that introduces the beta function of QCD that is nothing else than the derivative of the couplings of QCD with respect to the scale. So how does this coupling run is obtained through the, just by imposing precisely through the procedure that I described in words previously, and this is here illustrated in this sort of a side box. So how do you read this side box? So in this box here on the side, I've summarized for you the principle that through the renormalization procedure relate the original parameter of the Lagrangian, that is G sub S0, what we would call the Bayer coupling, to the renormalized one that is here on the right. This is the renormalized one. And they are related one to the other by a constant that we call the renormalization constant that we can calculate from our Lagrangian just in terms of the renormalization of the fields and the renormalization of the interaction. So if you remember, you take a term in your Lagrangian, which is the GS sub 0 times Q bar F. You take one of the terms in your Lagrangian. So if we go back to the Lagrangian that we were observing at the very beginning, the term I'm focusing on comes from Q bar F slash QF when I pick the interaction in the Lagrange. So when I pick the gauge boson term in the covariant derivative. So it's a Q bar F A QF interaction through the color and Dirac structure that is introduced by the standard QCD Lagrange. So all these terms are expressed originally in terms of Bayer fields and Bayer parameters, but if I now translate them in terms of renormalized field and renormalized parameters, so if I replace my original fields by fields that are now using the same notation, but imagine that you go back to the original Lagrangian and label by 0 everything that is in there. So in your original Lagrangian, you have tax as 0. My fields are now translated to renormalized field by a renormalization constant, both for the Q and for the A, a square root of a renormalization constant each, as you learn in QFT. And then the overall term that appears in front of the Q bar AQ interaction that I have here is the renormalization of the interaction itself, the interaction vertex itself. And this is what I define as a renormalized coupling times the renormalization constant of the vertex itself. Now, by equating A to B, I get the Bayer coupling as a function of the renormalized coupling, and I call Z sub G the relation. This is the renormalization constant of the coupling itself. Now, expressed in terms of constant that I can calculate from the renormalization of the vertex that I'm considering Q bar A, the renormalization of the fermionic fields that are related to the renormalization of the 2-point functions of the fields, and the renormalization of the gauge boson fields that are related to the renormalization of the propagator of the gauge fields. Renormalization of these objects means elimination of the ultraviolet divergences from the quantum corrections to these fundamental elements of your theory, the 3-point correlation functions and the 2-point correlation functions order by order in perturbation theory. So from these 3 elements, you calculate Z sub G. From Z sub G, you calculate G sub S, because those are obtained through a renormalization procedure. They are scale dependent, they depend on mu, and they allow you to calculate the derivative of G sub S with respect to mu, which you call the beta function of your theory. The beta function of your theory is therefore a perturbative quantity that you calculate order by order in alpha S, depending on how many corrections you consider in these 3 objects: 1 loop, 2 loops, 3 loops, and so on and so forth. So I can expand it and calculate these coefficients through the calculation of these 3 objects and this derivative. If I so do, I can get the first term with 1 loop calculation, the second term with the 2 loop calculation, and so on and so forth. And this is the fundamental and unique things that you really need to know about QCD for what matters in the following of our lectures. And it's the fact that if you do this calculation, you find this coefficient to have this value. So it's a number that is for the number of flavors we are aware of, which is 6, positive, but it comes into the beta function with an overall minus sign that is kept, and the other terms that I will add with higher order corrections are smaller than this one, so they won't change the sign that I find at the first order, and tells me that the beta function of QCD is negative. So that means that the coupling decreases with the raising of the scale, and it decreases with the lowering of the scale. And this is it. This is just the fundamental property of strong interactions that are such that at high scale, they have a weak nature, and at low scale, they have a strong nature. Where the name comes from, because first strong interactions were studied and discovered in nuclear interactions that are clearly low interaction, kind of low energy kind of interactions where the interactions is strong. But if we now look at the same kind of physics, the same theory, in a much higher energy regime, because of the running of the coupling, the theory is almost a free theory. Well, let's not call it a free theory, it's a weakly interacting theory. So it's the theory in which the fundamental objects of your Lagrangians, that are the fermions and gauge bosons that we have introduced as for any other non-abelian theory, and that in jargon we call quarks and gluons, are almost free objects. They very weakly interact one with each other. And the theory can fully be justifiably so treated as a perturbative theory. So with a perturbative approach. And this is the foundation of perturbative QCD. This is really why we have perturbative QCD, and also why perturbative QCD is so successful in collider physics. Because collider physics collides particles that can be leptons, so non-QCD interacting, but picking up QCD interactions after the collisions, or they can be hadron like protons, and they collide at very, very high energy. And by colliding at very, very high energy, they naturally collide in a regime in which we do not see the protons as such, but we do see the protons in terms of their constituents. So the bound states are dissolved at those energies, and they appear in terms of their fundamental constituents that are both valence constituents and C constituents. So they are, depending on the intensity of the collision, so the energy that I have available, there are an evolution of a large number of constituent partons, quarks and gluons that are present in the colliding hadrons. So this is no small thing. It's actually the reason why the 2004 Nobel Prize was awarded to Gross, Politzer, and Wilczek, and is where the story begins, really, with the parton model. So this is how we interpret hadrons at high energies. And as we will see in the following, this is really so fundamentally important in allowing us to calculate things at colliders, but not just on a back of the envelope calculation, in allowing us to calculate precisely, very precisely things at hadron colliders. Collisions at hadron colliders and the plus and minus colliders, of course, even more so, they are definitely structured and determined by the initial high energy collision, which is purely governed by perturbative QCD. Now, to give you the feeling of what this alpha S looks like, we can just look at the solution of these equations, and not in its entirety, but just at the first term that, as we said, is the most important one. There is where you look at, where you see the structure of the couplings itself and its dependence on the scale and which kind of dependence it has. And I think it's very instructive because it already brings forward some very fundamental properties of the theory itself, and some language too that we use, and some sensitivity to the kind of expansions that we typically use in the intrinsic to the perturbative structure of the theory itself. So if you take the previous equation and you expand it just considering the first term in the beta function, the alpha S squared B0 with a negative sign, and you solve this equation just by separation of variables, which is a very, very simple one, you get this solution. So it tells you that alpha S at a scale mu is obtainable from the evolution of alpha S at a scale mu0 through this analytic structure that has in the denominator 1 plus alpha S of mu0, so a correction of order alpha S, proportional to the B0, B sub 0 coefficient of the beta function, and a log of the ratio of the scale at which I wanted to evaluate mu and the scale where I start my evolution. So if you measure alpha S at a scale mu0, you can derive alpha S at a different scale via this formula at the first order, or via the more complicated formulas that in which this formula will morph to if we added to our differential equation, the B1, the B2 terms, and so on and so forth. I haven't specified it, but beta of alpha S is nowadays known up to the fourth term in the, exactly up to the fourth term in the expansion. This can be also cast. So there are two things that you see here. Well, first of all, is the behavior of the coupling itself. You also see something that is kind of interesting. That is, if you expand this same alpha S perturbatively, so if you treat this as small and you expand this 1 over, you will see that alpha S can, at a scale mu, is actually an expansion in alpha S at the scale mu0, and is an expansion that resum that contains an infinite towers of alpha S times log to the n, because it's the expansion 1 plus x to the minus 1, right? So alpha S in this form is often also referred to as alpha strong in the leading log approximation. And this is just the expression of what I just said, the fact that it contains, it resums intrinsically all terms of the form alpha S log of the ratio of the two scales. Now, these terms are small terms or large terms, depending on the ratio of these two scales. And this is a very important point that justifies for you the fact that in this case, as in a lot of other cases in which the very same procedure will be applied, the resummation or not resummation of those logarithms can be important depending on the presence in the theory that you are considering, so not in the theory, the presence in the problem that you are considering of very different scales or not. The other point that we wanted to make here, just to understand what is normally quoted in different results, is the fact that this very same expression can be cast into a more convenient one, or it's a different way, just by emphasizing the fact that we have a limiting scale somehow, in which the theory ceases being perturbative, stops being perturbative. So if I recast this formula by the definition of a scale lambda that we call lambda QCD, that is just defined by this equality, and that can be measured experimentally, of course, by measurement of alpha S, and turns out to be of the order of a few hundred MeV, so 0.2 GeV, depending on how many flavors you consider, depending on slightly different setups, but more or less it turns out to be of this order of magnitude. It tells us when this coupling becomes large. And that is, so when the scale gets, so when the scale gets closer and closer to lambda QCD, up to the unreasonable limit of being equal to that, and setting this coupling to infinity, as always in physics, when you see something going to infinity, it means that probably something is not making sense anymore. And what is not making sense anymore here is the perturbative approach to QCD, because the coupling is growing. So it gives you as a sort of extreme lower bound that you don't want to approach perturbatively. And this is the realm when perturbative QCD has to transform into something else, or has to be, unfortunately, not knowing an exact form of the solution of the Lagrangian of QCD, modeled by some hadronic model of some kind, as we will see. Now, due to the, for the sake of time, I will not go into any further consideration about another very interesting topic, which is the fact that the other parameters of the Lagrangian that has the masses of the Q species are also running parameters. I quoted just here for you the form of the evolution, and in terms of the equivalent of the beta function, that in this case is called the mass anomalous dimension, and expresses the variation of the masses with the renormalization scale. And as you may imagine, this is also a very interesting and challenging topic at the same time, in particular because masses in QCD are not, of quarks, are not well-defined objects, and for most of them, at least, except probably for the top quarks and probably a little bit for the bottom quark. And the reason for that is just that most of them turns out to be very close, if not below, the regime in which QCD is not perturbative. And so quarks do not appear, as we know, as free states. So they appear as bound state of hadrons, except for the top quark that lives long enough to be seen as a free particle before it decays, and never form a bound state. So here we see immediately that defining physical masses for quarks or on-shell masses for quarks is impossible, or defining an on-shell mass is an academic question. And that's the reason why typically schemes like the MS bar scheme that are also academic schemes and not related to physical properties are more convenient in QCD, because we don't have a real reason, like in QED or in electroweak corrections in general, to identify the masses of partons like leptons, of particles like leptons, so with the real mass. So I leave this as a side topic. Just remember that mass is runs, and in some cases resumming corrections due to the running of mass can be very important. And this is all true both for, in particular for quarks like charms and bottoms that are at the threshold, right, between perturbative and non-perturbative QCD. Now,
Laura?
Yes?
There's a question from a student in the chat.
Sure, go ahead.
May I ask how alpha S runs in some dynamical system? For example, when the universe is evolving, the energy scale is changing. How should we put alpha S into the equation of motion?
Well, that depends, I think, on how you are. So is your system, right, affected by QCD, first of all? This is the first. How are you mapping perturbative QCD effects into the description of your problem? That's a fundamental question. Once you know that, then you'll be able to evaluate which level, at which level the running of alpha S affects your problem. And the running of alpha S affects your problem, first of all, in evaluating at which scale, for instance, you want alpha S at which scale enters your problem. And once you know that, you can obtain the alpha S that you need at the order that is reasonable to the problem that you are considering. Of course, the question is very general, so it's hard to say anything more specific without really looking at the specific of what you want to calculate. Does this answer at least barely your question?
Yep, they say thanks.
Okay. So just as an illustration of the running of alpha S and the fact that this academic point of solving, after all, simple differential equations and seeing that indeed alpha S runs. Is it proven? Is it verified in nature? And well, I took these a couple of plots from the particle data book, just because they are the most updated one. A very recent version just came out in June of this year, so it's really fresh out of the print. And here you see in the first couple of plots a myriad of different determination of alpha strong that tells you how alpha strong is measured in very different processes, physical processes. In tau decays at low Q square, on the lattice, on QQ bar bound state that is also low energy. But then you start measuring it in deep inelastic scattering experiments, a little bit higher energies, quite substantially higher energies. And then in E plus E minus interactions, even higher energies, hadron colliders. This is a relatively not new entry, but let's say the degree of precision with which alpha S can be measured at hadron colliders is kind of increasing and improving. And you can see these on the right-hand side plot, where, as you may notice, there are a lot of entries from ATLAS and CMS, LHC experiments. This is an incredible achievement, because it tells us that, as it is represented in the plot below, you measure the evolution of alpha S from energies of the order of 1 GeV, so barely above the non-perturbative threshold, to 1,000 GeV, so to the TeV scale. So there are orders and orders of magnitude over which the evolution of alpha S within the errors that are sometimes larger, sometimes very, very small, is consistent. And this is, of course, here is why I put this formula here at the bottom, which is the relation between alpha S with a given number of flavors, NF, and alpha S with a number of flavors plus 1. And the reason why I put this formula here is just because, as you may imagine, in going from here to there, you go through thresholds in which you have in this region the charm quarks come about, but then you have a bottom quark, and then you have the top quark higher up. And alpha S doesn't stay the same because it depends on NF. Lambda QCD also depends on NF. So alpha S depends on it. And however, perturbatively, just you can calculate exactly the matching between below and above the threshold and get a relation that expresses alpha S in terms of knowing alpha S with an F flavor. It gives you alpha S with an F plus 1 flavor, and you keep going. So this is taken into account into this evolution that matches beautifully what is seen in nature. So what is seen in experiments that covers the entire spectrum over which we would like perturbative QCD to work.
Okay,
now,
there's a couple more questions when you have a sec.
Sure.
The first one is, these processes are happening at different energies, but they're measuring alpha sub S at mu equals mz. So they're using RG running to adjust their measurements to obtain alpha sub S at mz.
Yeah, that's so these processes are measuring alpha S at different energies, as you see here, and they all converge to this value of alpha S of mz by evolution. Yes.
Okay, and then the next question.
The top picture, Laura.
Sorry?
The question is about the top picture on your page.
Okay.
That one.
Okay, the next question is, I see you define NF as the number of light flavors. Does that mean NF should be flavor scheme dependent?
Alpha S, you mean?
NF, the number of flavors.
The number of flavors is the number of flavors, yes. So it assumes different values depending on the energy which you are. Oh, okay. The number of light flavors. That's probably what is confusing. So the number of flavors that you can assume that are treated in the evolution of alpha S as light flavors. Yes. So it varies with the scale at which you are.
One more question just came up. The bottom plot, the measurements are at different orders. For example, next to leading order, next to leading order. How can we put coupling and different orders into the same picture?
Well, that tells you that, of course, depending on what you're using to measure alpha S, you may know that particular observable at a higher or lower order in QCD, because corrections have been calculated at a higher or lower order. That means that the extraction, depending on the order of which your calculation is done, you will extract alpha S with that level of precision if you want. So your calculation will be fully, you can, right? You just extract the alpha S, the measure of alpha S of that particular, from that particular observable will probably be better than the measure of alpha S from a process that is not well understood from the point of view of perturbative QCD, given that we are trying to extract here a parameter that is a fundamental parameter of perturbative QCD. So yes, you can of course use the things that are that have been calculated at different orders. They will be typically better. The extraction of alpha S will be probably more. It's not the only consideration in the extraction of alpha S. A lot it depends on the observable itself. There may be observables that are more or less sensitive to QCD corrections, but in general, you say you would get a better extraction. Yeah.
Okay, it looks like that's the last question for now.
Okay, so with this in mind, let's come to the crux of the matter, which is this, where we really apply perturbative QCD calculation. And here is where I was, my notes would still need some improvement in being drawn. So let's draw the picture that I would like to draw here together. Also because I think it makes more sense to draw it together and see it growing with us instead of presenting you with that picture, because you don't really know where it starts and where it ends, right? It's all together, but we go in steps in understanding it, right? So far we have convinced ourselves, or at least I have reminded you why we take why a perturbative approach to strong interaction in certain regimes, typically the high energy regimes, are very well justified. And so we want to use that in particular whenever the perturbative regime is the dominant one, which is in high energy collisions, for instance. And given that you are going to have soon today lectures on collider physics, I think this is most appropriate, even for you to make sense immediately of things that you hear in different contexts. This is not the only context in which perturbative QCD is important. You can find important applications of perturbative QCD in many other regimes. You can look at flavor physics. A lot of the result and the structure of flavor physics is dominated by perturbative QCD evolutions of at least perturbatively dominated evolution of QCD effects. But I would say that the prototype example of how a perturbative QCD calculation is structured really comes from scattering processes at high energies. And that is what we want to focus on. So let's build it in stages, and let's build it for a hadron-hadron collision, which you may think, well, that's, if we started from any plus and minus collision, that would be much simpler, because plus and minus are not strongly interacting, so QCD has to come in later, and at least my initial state, I know exactly which particles I have. They are elementary particles already. They're not composite states. They don't have QCD interaction, so I can forget about QCD interaction in the initial state. I know exactly their energies. But at the same time, if we understand the other picture, of course, as a particular simple limit, we will also understand the plus and minus picture. So we have two hadron colliding. Let's say two protons, so just to make the LHC case. So you have these two objects, a proton and another proton coming in your collisions. And at this point, the first thing that you already know is just that they are bound. These objects, they are naturally at low energies, bound states of constituents, and the constituents are quarks and gluons in the Parton model. But by the time we collide them at high energy, they are not anymore bound state of quarks and gluons, but they live in terms of their constituents. So their nature is indeed in their constituents. And what really makes up the high energy interaction are the interactions among their constituents. So to make our life easier, let's start picking one constituent on each side and see what happens to that constituent. So there are many constituents in here, right, in each one of them. And most of them will just form a sort of uncorrelated kind of mess of soft QCD interactions, not particularly with that exchange without a particularly high energy exchange of momentum exchange. But among them, in particular, if we go to very high energy, a very large number of them, small compared to the total, but still quite large in terms of the statistics that we wanted to accumulate in order to have a meaningful result, will come out with colliding one with the other with a high momentum transfer. And this is precisely what we define as hard scattering. So we will have a parton coming out of here and a parton coming out of there and colliding here with the hard scattering. So let me use maybe a different color here. This would be our region of hard scattering. So this is a region in which perturbative QCD is clearly the dominant player. And it's dominant player because it's high energy, the coupling is small. So this is a part of the story that is entirely determined by perturbative QCD. Now, this is clearly not the end of the story, because you know that as you started from hadron, you will end up in the final product of your scattering, not with quarks and gluons that may come out of these scattering process with a lower or higher multiplicity, depending on the process that I'm focusing on. We will not measure these objects in the final state, but what we will really measure in the final state will be hadrons. So will be again leptons as well, but from the QCD part of the story, we will measure in the end bound states of quarks and gluons due to the fact that from the original core of the hard scattering, the energy deteriorates to a point where it is low enough to prevent you from using perturbative QCD and from entering the regime of non-perturbative QCD and therefore confinement of fundamental degrees of freedom of quarks and gluons into hadrons. So how this happens is through perturbative QCD interactions. And it happens through perturbative QCD interactions both backwards when we go from the hard scattering region to the original protons and forward. So when we go from the hard scattering to the final state that here I haven't drawn, but let's put it out here. Out here we can imagine to have a lot of hadrons. And some of the hadrons will be maybe grouped into what we call energy depositions of jets, but there will be jets of hadronic states. So for the moment, let's just imagine these objects as bound states of quark and gluons that then can be grouped among themselves if they are particularly close and form jets of hadrons. So going from the hard scattering to the initial colliding protons, or from the hard scattering to the final state hadrons, is a process that happens through perturbative QCD. And it happens through perturbative QCD all the way till it's justified energy-wise, right? So it will be branching of a quark emitting a gluon and a gluon emitting other gluons and a gluon splitting into quarks and so on and so forth. So all these branchings will happen till the point in which by the time we reach the hadronic energy level, they will be lumped and confined into hadrons. So why do I draw this picture? Because, well, here we see clearly stages, these blue stages here, where hadrons are present at the beginning and at the end, that are clearly non-perturbative, right? So this is non-perturbative QCD at play, sorry. But the evolution to these states is perturbative QCD. So perturbative QCD will give us a way to evolve from the hard scattering region all the way down to the non-perturbative QCD regime of the final states, and all the way back to the non-perturbative QCD regime of the original protons, where some modeling will have to come into place. And the interesting thing that we will see, just based, so this picture by itself is already based just on the nature of QCD as we have reviewed this morning, just asymptotic freedom and confinement. Now, the structure of which this evolution backward and forward happens, and therefore the structure with which I expect to see things in my final state will be dictated again by some simple, relatively simple property of QCD, which we will learn by studying these patterns of pattern emission. So how does a quark split into a quark and a gluon, or a gluon splits into two quarks or two gluons, and so on and so forth? Is that something that happens with certain patterns? And do these patterns justify or explain the kind of structure that I see? All that is perturbative QCD. So perturbative QCD also lives in the evolution of my original hard scattering process backward and forward. And this is what also we will see, not today, but probably tomorrow. Now, there is much more that we can add to this picture. And if you see some artistic rendering of these very same pictures that people often use to illustrate, particularly when using slides in their talks, of course, they're beautiful and they contain much more information. But at the same time, you justify too many things at the same time, right? So just to tell you what else we're missing here, well, we're missing these kind of dynamics. So underlying events, soft events that are all around. And of course, when you get to some level of precision, you have to have some careful way of either modeling or measuring the effect of these things if you wanted to extract with the great precision the part that you best have under control, which is the hard scattering part. There is if you wanted the possibility that you have more than one hard scattering, what is called multiple scattering, or double scattering, triple scattering. That's also something that can produce the same final state you're interested in. So as you have one here, you can have another down here, and so on and so forth, right? Typically, they're really higher order if QCD, here, this is the perturbative regime. These, having two of them is higher order than alpha, so it should be a smaller contribution to a given process, but it's a refinement of your prediction that you may take into account, and much more. But of course, on the span of the time that we have, to understand how perturbative QCD plays a role in the hard scattering, in the evolution, and in the overall theoretical prediction of such a process that also has a non-perturbative component to it. So justifying why that non-perturbative component doesn't take away from the precision with which we can predict a certain observable set colliders would be already a great goal. And let's have it as a goal. So to illustrate my point, and I don't have much time left, but at least let's get started on what I would like you to guide through between today and tomorrow, is that today I was planning to focus on this part, on the hard scattering part. And in order to focus on the hard scattering part, I needed to give you some idea of what enters in calculating the hard scattering part, including higher order QCD corrections, because that is what it's about. So the hard scattering part is the parton level process. And the parton level process is calculable in QCD at the order at as high as technically we can, or as high as needed. So this is probably the most important thing that I would like to convey to you. So the fact that as high as needed is something that by the end of this series of lectures, we should be able to gauge and we should be able to understand, which is very important. At the same time, I need to tell you how you do it, starting from the first order. And because QCD is complicated, we wanted to take away some of the non-necessary complications to understand certain things. And the part that we wanted to take, in order to do that, we at this point go back to maybe any plus minus process instead of a PP process, so that for the moment we can really forget about the initial state. We can really imagine that these two objects coming in are E plus and E minus, and there is no perturbative QCD in the initial state, and there is no non-perturbative QCD either in the initial state. It's just a particle coming in, two elementary particles coming in with a very well-defined energy and momentum. So let's go back to a process that is an E plus E minus process. And an E plus E minus process that, however, resemble this one in the final state. So why not E plus E minus 2 hadrons? Now, the reason why this process has been so crucial, it's used so much in discussing. Let me ask for. Can I use a few more minutes? So that for me, like 5 or 10 minutes.
Yeah, I mean, you started late, so yeah, just please.
Okay,
yeah.
just for me to know where, for what to aim.
Yeah. We've typically been going 5 to 10 minutes over anyway with the question period, and there's a half hour in between lectures. So as long as the students get like 15, 20 minutes break, then I think we're good.
Okay, thank you. Thank you very much.
Thanks.
So E plus E minus 2 hadrons is really important, and you see why pictorially is important, as I was explaining, because it's exactly what we have here, except from the initial state complication. So it could give us very good guidance. It is also something that has played a really important role in QCD from the birth of QCD itself, right? Because if you remember, one important object that proved or gave evidence for this n equal 3 gauge quantum number of QCD was the ratio that we call R between the cross-section of E plus E minus 2 hadrons and the cross-section of E plus E minus 2 mu plus mu minus that you calculate in QED, right? So this cross-section turned out this ratio is proportional to the sum of the charges of the quarks that appear in the final state. So this cross-section is calculated. So this turns out to be proportional to the number of colors and the sum over the charges of quarks square plus other terms. And this is just two important things. One, that this is true only if this can be calculated in terms of parton states. So it be calculated in terms of this process at the first approximation. And it is true only if this n is equal to 3. So if it's equal to the number of colors. So it turns out to be what it is only if there is such n, and if such n is equal to 3. So this was one of the first important evidence for the gauge structure of QCD itself, both in terms of the non-abelian nature of QCD itself, that is fundamental in proving the possibility of a weak interaction at high energy. So this process. At the same time, this process, E plus E minus into hadrons, is, and this probably at this point is not so meaningful to you, but it's very inclusive. And this is and what that means is just that we are not so picky about the final state. We just say plus E minus into everything, basically, and in particular into all possible hadrons, without specifying how many we see in the final state, how many, and grouped how in the final state. So this is typical. It's an important property, as we will see and justify after seeing what we're going to see. It's an important property that will allow us to obtain physically meaningful finite quantities from a QCD calculation without introducing anything more than our understanding of the properties of quark and gluon emission. So let's see, and this is how I wanted to conclude this lesson, and we will go to the details of it at this point, I would say probably tomorrow, but I wanted to give you the introduction to it so that maybe you can start thinking about it and you can even start calculating a little bit things on your own. So if we wanted to calculate the sigma of E plus E minus into hadrons, and from what we said before, the real process I'm interested in is to calculate the sigma of E plus E minus into QQ bar plus QCD corrections. This is what I wanted to do. So at higher order in QCD, bringing in QCD corrections. So let's make it very simple. And for the moment, let's imagine that this process is just this simple process here, mediated, let's say, by a photon. It could be a Z too, but let's say it's just a photon. And these are E plus and E minus. So this is E minus, this is E plus. So this cannot be anything else than a gluon or a Z boson. So let's take a photon or a Z boson. So let's take a photon. And that goes at the lowest order in QCD into QQ bar. So this is my process to start with. This is what we call the tree level, or the lowest order is the first order at which a process appears in a given interaction. So in QCD in particular, this is as low as it gets because there is no QCD in this process to start with. So, and this is the beauty of having considered this process because it's not too complicated to start with. So QCD comes in at the moment in which I add QCD corrections. So the first order of QCD corrections. And the first order of QCD corrections is made now, and you probably remember this from your classes, but this is the point where probably different kind of backgrounds start differing depending on how much you have seen of QCD, but probably you have seen this in QED. So in QED itself, if you had to calculate QED corrections to this process, you would add both virtual and real corrections. So you would consider the contribution to the cross-section of this process of order alpha E in the case of QED. In the case of QCD, we consider the contribution of order alpha S. Why do they come from both virtual and real correction, and what are virtual and real corrections? So for this particular process, and as far as QCD is concerned, it's clearly we can just focus on this part of our diagram, because E plus and E minus, at least at the first order in alpha S, they don't see any QCD interaction, right? So because of that, and if we consider only photons, right? So because of this fact, let's then work out the first order of QCD correction by considering just this part of the diagram and divide them up into what we call virtual and what we call real. They're virtual because the process is virtually the same. Well, let me draw it this way. So the process is virtually the same, but there is an exchange of an order alpha S interaction among the constituents of the process. So the process is a photon splitting into a quark and an anti-quark. So what can happen is the exchange of a gluon. Technically, I could also have to consider reabsorption of a gluon on one of the constituents themselves that are coming out in the final state, the quark or the analogous diagram for the Q bar, plus the analogous diagram here. Now, I put this in parentheses because depending on the renormalization scheme that you have chosen, depending on how you do your calculation, these objects may or may not contribute to your cross-section, but technically they are there. They are corrections that you have to include, virtual corrections that you have to include. The final state does not change. This is a 2-to-2 process. It stays a 2-to-2 process. It acquires an order in alpha S because of the two GS proportional vertices. Now, this will give a contribution to the cross-section of my initial cross-section here, including QCD correction, that is of order alpha S. And it is of order alpha S when I build the amplitude for this process. So my M222, M is my amplitude, scattering amplitude. My scattering M222 amplitude will be made of a tree-level contribution, which is this one, and let me call these M0 222. But there will also be an M1 222, which is the order alpha S corrections, the order alpha S contributions to the same final state, to the same QQ bar. Now, at the level of the cross-section, I will build the contribution to the cross-section. So this will go into the sigma by integrating over phase space of the 2-to-2, integrating over the phase space of the 2-to-2 process, the matrix element square of this guy. And of course, integrating the matrix element square at order alpha S will imply keeping only two of the terms that appear in here, that are the M0 2-to-2 square and the interference between the M0 and the M1. So the interference between this diagram and these diagrams. So the, let's say, M0 star times M1 plus M1 star times M0 of the 222 process. And I leave out the M1 222 square because this object here is already of order alpha s square. So it doesn't belong to my calculation. So this is what we call the virtual cross-section, the virtual part of my cross-section. Now, on the other side, I have processes that, technically speaking, they do not belong to the same final state, or they seem not to belong to the same final state, but they give a similar contribution to the cross-section, where similar means the same order in alpha s. And these processes, for the particular case of QQ bar, are the processes of gluon emission. So if I consider this process, where either Q or Q bar emits a gluon, this process will give me an amplitude, a scattering amplitude, that is a 2 to 3 scattering amplitude, that is technically not yet of the same order. So this is an order, I have to go back to G in order to express the order. It's order GS cube, right? But by the time I build this into a cross-section that I will call the sigma real, this will be proportional to the integration over the phase space of the 2 to 3 process of my M2 to 3 matrix element square. And this object here at this point is of the same order as sigma virtual. So this will also be of order alpha s. Sorry, this is of the GS for this process. This is of order alpha s. Okay, so why can I and why do I have to consider these two processes together? The reason why I can is because of the inclusiveness. So as we said, this is a very inclusive process. So E plus E minus into hadrons will receive contributions from all these processes. E plus E minus into hadrons is nature. Nature doesn't know if my hadrons are coming from E plus E minus to QQ bar, E plus E minus to QQ bar plus a gluon, E plus E minus into QQ bar plus any number of other patterns. The important thing is just that there are hadrons in the final state. So from that point of view, not only I can, but I have to include everything that can contribute to this process at the same order in my perturbative expansion of the observable, which is the cross-section, right? So the thing that we will see a posteriori, and that at this point we will see tomorrow, is that these two processes, so these two different parts of the calculation, these two different parts of the cross-section, what we call sigma virtual and what we call sigma real, that will constitute the final result. It will be the sum of the two. They have another very important property, and is the property that other kind of divergences that appear in the calculation that we have not seen here yet, but that we will see tomorrow, that are called infrared divergences. So divergences when some of the energies goes to zero, some of the angles goes to zero, and in particular, which energy and which angle are the energy and angle related to the extra pattern that we are adding in adding the order alpha s corrections, just because the first two Q and Q bar are hard patterns that are coming out of the hard cross section, so they have a lot of energy and they're well distinguished one from the other, so they're well separated. But the extra pattern that I either emit and reabsorbed in the virtual correction or emit as a real pattern has its own energy, so it is coming out with some momentum k here, so it will have its own energy, right, in the k mu momentum, and will come out with a given direction of the momentum with respect to the emitter, with respect to the quark, or with respect to the anti-quark, so at a given angle. And as we will see in the calculation of the scattering matrix element, these two elements, so the energy of the pattern and the direction of the pattern that is emitted, that can be translated into integration variables over the loop momentum of this virtual pattern as well, where we can also identify an energy and an angular variable in the integration over the loop momentum of this object, can go to 0. So we say that this object can be soft, or can come out with an angle that tends to 0. So they can come out parallel. The emitted pattern can come out parallel to the emitting pattern. And in that case, we call it a collinear divergence. In both cases, the amplitude, in particular the integration over the phase space of this amplitude is divergent. And the integration over the loop momentum of this object is divergent. They're both infrared divergences. They're infrared divergences analytically of exactly the same nature. And so mathematically, they have to talk to each other because in the limit in which the energy of this object goes to 0, or the angular variable that parameterizes momentum with respect to the quark or anti-quark line goes to 0, they become the same thing. They become the same process. So they have to talk to each other. And as we will see, they do. And they do in such a way that they compensate exactly one another in such a way that the final result is infrared finite. Now, I leave you with these 2 observations. Well, 1 recommendation and 2 observations. The recommendation is just to have a look at these processes. And if you have a little bit of time, try to think how you would calculate this object and try to think how you would calculate this object in terms of when built into a cross-section, and try to calculate how you would calculate the emission of an object that has small energy or small angle in the case of the real emission, and how you would build that limit of the real emission cross-section. The observations that I want to leave you with is just that we're not doing these just out of reviewing a QCD calculation in some level of details. But just because the study of this infrared problem, it's really extremely important in order to understand how we identify good QCD observables, 1. And 2 is fundamental to understanding the dynamics and the structure of QCD processes. So it's something that will dictate for us quite substantially the structure of these backward and forward evolution that we have here claimed. It is determined by perturbative QCD. And in order to understand why that is the case, we have to go through this step of the calculation with some more details than just saying, oh, this is infrared divergence, this is infrared divergence, the divergence is cancelled. We have to look at these divergences and we have to see this happening, maybe not in the gory details, but at least structurally. We need to see where it's coming from. And therefore we start from, I would say, in tomorrow's lecture. And this is actually a very good point to start tomorrow, because we will see this emerging at this level. We will see it canceling when we are inclusive, and we will see how, for the exclusive case, when we are a little bit pickier on what do we pick as final state and we don't take everything that comes about, we will have to modify our approach, taking into account what is the leading dynamics. And we will see that the infrared dynamics, particularly the collinear dynamics, will be the leading one, and will structure both the backward and the forward evolution of our process. So it would be a nice connection to see it happening first in the case in which everything maps to a finite quantity, and then in the case in which we have to do something in order to map it to the initial state and final state evolution in order to reabsorb collinear and soft divergences into well-defined physical objects. So I'll stop here for today. Thank you for your attention, and sorry for having gone a few minutes late.
Oh, thank you, Laura. Given the time, and I think we want to give the students a break, Laura, are you available to join the coffee break later today?